Okay, so let's consider a collision between objects, say of mass m star, moving to the right with a speed v naught, and an object of mass m star that's moving to the left with speed v naught. Okay, so we know that before this, from a Newtonian perspective, we have a momentum which is m star v naught, I hat, say, for this one, and then we have negative m star v naught I hat for the other one, and so the total momentum before the collision is zero, and after the collision it must be zero as well, and so the particle, the combined system looks like that, and we say that the mass is twice. That's a Newtonian analysis. Right, so we want to move towards understanding this in terms of relativity. We want to argue that we can see that the correct relativistic version of this analysis involves adding the four momenta, or actually adding the two momenta in this case, because we're in just two space-time dimensions. So if we consider this same kind of thing, but from we'll do the analysis from this perspective. Right, we're in a frame in which both of these are moving, but if we get into a frame where, for example, this one isn't moving, so we're following this one to the left, then we see this one moving towards it at a greater speed. So in that case, we would have something like m star moving this way at 2v naught, and this particle just sitting there. And so the momentum beforehand would be 2m star v naught I hat, and afterwards it would have to be the same. So when we have a collision and the two systems move together, they would have to be moving that way. So let's look at this from a relativistic perspective, and let's see that, in fact, we want to add the two momenta. We won't argue from first principles mathematically that because the Lorentz transformations are linear, that's a reasonable thing to do. We'll just sort of check that they work. So if we think of the system like this, then we have the particle on the left has a two momenta, PA left, which looks like, right, we have the energy term, so we have the mass divided by the 1 minus speed squared term, square root. Right, we have the energy term, and we have the momentum term, the m star v naught over 1 minus v naught squared, and that's the two momenta of the particle on the left. Then let's write the two momenta of the particle on the right, PAR. That's similarly to that, m star over 1 minus v naught squared, and the other term just has a minus sign here. So let's see what we get if we add these two. So if we add these two, if we do PL plus PR, then we get twice m star over 1 minus v naught squared, square root, and then of course we get 0 here. And so we are in a frame where the newly formed object isn't moving, and so this actually is, the entire thing is the rest mass of this new object. Right? It's written in terms of some velocity here, or some speed here, but the entire thing is just now an object at rest with that rest mass. So the rest mass has increased and the momentum is 0. So that at least looks reasonable. Now let's look at this from the other perspective. From that perspective, of course, when we do, if relativity holds, we do Lorentz transformations on the speed of this object, and we get something like VI bar. We're looking at it from the perspective of the observer that's moving with this object. So this object seems to appears at rest. So the other object will have a speed which is given by v plus v naught over 1 plus v naught v. And of course the v is v naught, so we get 2 v naught over 1 plus v naught squared, if I did that correctly. And after the collision, of course, from one perspective it's 0, and so from the other perspective that needs to simply be v final bar is v naught. And so let's write PL. Thinking, let's see if I need another sheet here. But the first thing to notice is that these are the Lorentz transform components of the velocity, and I can't just throw in the mass here. Right, so this is the momentum would not be conserved if I just throw in the mass here. So let's look at this from the perspective of two momenta. So I have P, the particle on the left now, PL looks like, so I have the mass m star, right, the particle is coming in, and I have, so this is the energy term. I'm going to be dividing this by 1 minus the speed of this particle, which is this, right? So as I call it VI bar squared, square root. And here I'm going to have m star VI bar over 1 minus VI bar squared, square root. And so we can plug this into here, and the other term, PRA, P, the right particle on the right, has an energy term that's just a rest mass, and then 0 momenta. So we need another sheet. And so let's add these two terms. So I'm adding PL and PR from a different perspective, a different reference frame. And so this is going to look like m star over 1 minus this VI squared square root plus, right, this one just has the m star in it, and the momentum has just one term. And so we can work this out and see what it gives us. And once I plug in that VI that I got on the previous page, I'll end up with a term like this. And here I'll have a term like this. And I want to argue that we could have gotten these terms by simply recognizing, and therefore showing that there's consistency here, that we want to think of this as the rest mass divided by a term that goes like 1 over that goes like dividing by a term that is the square root of 1 minus the speed squared. And so let's go and look at our rest mass from before, right? We know what the rest mass is of the particle when we looked at it from the perspective in which the particle wasn't moving. That rest mass was 2m star over 1 minus v naught squared square root. Right, so that whole thing is the rest mass, and so we want to think of dividing that by a term that involves the speed, but that's the same speed, so a term like that. And in fact, thought of like that, we can see that we expect this to equal to that. In fact, that translates into that, but we can sort of see physically that this is consistent with the idea that it's the rest mass divided by term 1 minus the speed squared square root. And similarly here, we can just think of this rest mass times the velocity in question, which is this, right? So we have a 2m star over 1 minus v naught squared square root term. We multiply, that's the rest mass, we multiply it by v naught, and we divide by a 1 minus v naught squared term, and that should reduce to this. As in fact we see that it does. So we can see that we've argued that there's consistency in this procedure so that in a collision it's really the two momenta, or more generally the four momenta, that we want to add together.